Hi, welcome everyone. I'm going to be talking about bootstrapping today, but before we talk about bootstrap, I just want to touch a little bit about cross-validation. Cross-validation and bootstrap are sort of similar methods, but the difference between cross-validation is that you can basically what is bootstrap is cross-validation done multiple times. It's called bootstrap. So let's look at this example. So as we increase in cross validation has to be done multiple times to kind of make something similar to a bootstrap concept. So cross validation can be done in different ways. For cross validation, you can given one data set, you can create a validation set and use some part of the remaining part as your training set and do one method of cross validating it that way. The other way would be to use leave one out leave one out cross validation, or you can also do k-fold cross validation. In k-fold, what you're doing is, given a data set, you split the data set into, say, like if you have 100 elements or 100 points, you say every fold is 10 points, and then you train based on that. But the problem with that is that when you're training and fitting a model in a k-fold, you tend to use less data while training. So always when you use less data when you're training, you um, if you use less data, then you have increase in bias and decrease in variance. But at the same time, if you increase k, which means if you go, say if you have 100 points and your k is, you want to split it into 10 sets, then 100 divided by 10 would be, you would have 100, you would have 10 points in each fold. But say if you increased k from, instead of 10 folds, I want to do let's say I want to do 20 folds. So how much data is there if you how much data do you have in each fold? You would have 5 data points, right, in each fold if you increase k. So the plot, as you can see, let's look at the plot a little bit here. So what we see is that as you increase the size of the training set, which means if you're training on a lot of data, you actually decrease bias, because whatever you estimate it to be, your suggestion is not biased. Basically, that's why we say that when you increase your data size, if you train on the entire data set, or if you train on close to the entire data set, then you're decreasing bias, but you're increasing variance, right? This comes in relationship to the bias variance trade-off. So in k-fold, as you increase, so if you go from k equal to 1 to k equal to 10, you will be increasing and decreasing the bias and variance, right? So look at this plot. As you can see, the size of the training set, say if your size of the training set is 200, right, and you decide to do a 5-fold cross validation. So 5-fold means you're taking that 200 samples that you have and you're splitting them into 5 buckets. So how much will each bucket have, right? How much will each bucket have? Each bucket will have 40 points, right? But the point you want to know, or it will have probably like 4/5 of your data will be in the training and 1/5 will be treated as your test, right? So if you divide it into 4/5. Now the point you want to see here is that 5-fold cross validation has little bias on a data set of 200, because if you look, what this plot is showing you is the number of size of the training set versus the 1 minus the error rate, which means the accuracy, how much accurate it has been, how much accuracy can be generated, right? So in a 200, when the data set is 200 and say you go, instead of doing 200 you use 160, right? Because you give away one fifth of your data set as training. So there's not much difference if you read this graph at 150 versus 200. So even if when n is large, and it doesn't make a huge difference, you're still getting accurate. But if you have a very slightly lower n, you have slightly lower n, and you try to do cross validation, and in this scenario if you divide by 5, your training set is reducing by 4/5. It's only 4/5 of 50, right? Which is, but when you read the graph over here, you'll see that there is a huge difference. So 4/5, there's a huge difference between reading the graph at 50 versus reading the graph at 25, right? There's a big, the curve is happening at that point. So hence we say that as we increase k, we decrease the bias, but we increase the variance of the cross-validation error. So now let's talk about Bootstrap. The main topic I want to talk here is Bootstrap. So what is Bootstrap? So Bootstrap is providing the standard error of the estimates, right? Bootstrap is a technology or a technique that lets you calculate something multiple times such that you can determine the standard error of that particular estimate, or that statistical thing that you're trying to learn about, whatever the statistics metric would be, right? Maybe it's the mean, and or maybe it could be the variance that you're trying to understand of the population. But Bootstrap will let you do multiple on different sample data sets by just reduce them by indexing or subsetting the data and running it multiple times, and it will enable you to get a standard error on that metric that you're talking about. So one of the most important techniques, this is one of the most important, but it's very computer intensive method. So back when it was invented in 1980s or so, it was hard. It was only invented at that point because that's when computers started existing and stuff like that. It was introduced by Brad Efron, who was from Stanford, and I believe he's still a professor there. So standard errors in linear regression. So imagine we did a linear regression, right? And we get standard errors for each of the variables or parameters or predictors, right? Whatever you call it. So standard error is the standard deviation of an estimate from the sample size n, right? So in this you say that the coefficient for CRIM is equal to the estimate, and also you get a standard error. But this is only for one execution or one possible run, right? Imagine if you wanted to compute this such that your standard deviation is close to the actual population standard deviation. That's where Bootstrap comes in handy. So classical way to compute Bootstrap errors is to compute the standard errors is you would estimate the variance, and then what is the standard error of the variance, and then you would estimate the standard error of the sample variance, right? So to estimate the standard error, you would assume that the points are normally distributed. You would assume that the true variance is close to the estimated variance, and the true mean is close to the estimated mean, and you also assume that chi-squared n-1 has then the variance then -1 has a chi-squared distribution with degrees of freedom. This as standard dev is the standard deviation of this sampling distribution is the standard error, right? So how much is the deviation? That is the standard error. But the limitation with this approach is oftentimes what happens is the distributional assumption breaks down. One of those assumptions, say for example, out of the 4 assumptions, the assumption that we said is normal, that breaks down. Then you cannot do that. Then you cannot derive the standard error based on the standard deviation. And or you might the estimator does not have a simple form, and its sampling distribution cannot be derived analytically. So then you need something more robust to be able to determine this. So let's take an example here. you're investing in two assets. Suppose X and Y are the return of two assets, right? These returns are observed every day and you have them plotted over here. So let's say these are 50 points plotted here. We have a fixed amount of money to invest, and we will invest in a fraction of alpha on X and a fraction 1 minus alpha on Y. Therefore, our return will be alpha times X plus 1 minus alpha times Y. Our goal is to minimize the variance of our return as a function of alpha, right? One can show this is optimal, that optimal alpha is obtained with this formula. Now, the proposal we have is use an estimate, right? We're going to estimate the standard deviations. Now, investing in two assets, suppose we compute an alpha estimate of 0.5 using the samples. But once you have computed it, how sure can you be of it? I mean, you've just done one simple execution, right? Can you be sure that this same scenario will happen 100 times? Do you have an assurance? You don't have that assurance, right? So in this thought experiment, we know that the actual joint distribution, and we can resample the n distributions to our heart's content. But usually in real life, you need some assurance, right? So resampling the data from the two distributions. So what you can do is, if you have lots of data available to you, you can keep resampling from the data from to get to the true distribution, right? Now, computing the standard error of alpha. How would you have done it if you were to compute the standard error of this alpha hat that we estimated? Standard error of alpha hat is approximated by the standard deviation of these values, right? As we said, in reality, but the problem here is, in reality, the data is very limited. We don't have indefinite or infinite amount of data. So when data is limited, with the data you have in hand, you have to make the best use of it by probably running your running your techniques on the same data multiple times so that you can get assurance or guarantee. This is where what is Bootstrap, right? However, these samples um, approximate to the joint distribution. So let's look at Bootstrap now. Bootstrap resample the empirical distribution. What does Bootstrap do is, Bootstrap allows you to resample from the given data or the empirical distribution. Basically, you're taking some values of xi each time, right? So if you have a data set of 100, you'll run Bootstrap first time, which will pick randomly 10. Next time another random 10. So there's so many combinations of 10, 10, 10 you can pick, and that's where Bootstrap has the benefit. And you can also equivalently resample the data by drawing n samples with replacement from the actual observation. So you can do it two ways, without replacement or replacement. So look at this, the schematic of the Bootstrap, right? So this is the original data. You have the original data. What you would do is, you would take the original data and you would split the first Bootstrap will pick the data sets 3, 1, 3 and give you an alpha for it. The second Bootstrap will pick another random 3 points, which would be 1, 2, 3. And the third and so on will pick, and then each time you get an alpha estimate, right? And Bootstrap will take those alpha estimates and give you another average of those alpha estimates. That way you're assuring or you're guaranteeing that we have run this process 1,000 times and this is the number we finally come up with, and hence this is the standard error. So then you can find the standard error and you can assure that it will be within a set of this is the possible values that it can go. You can build a confidence interval for the statistics that you're doing. So comparing Bootstrap resamplings to resamplings from the true distribution, right? So in this, as you can see, that the true distribution, look at the rightmost, the graph on the rightmost panel. You can see that the Bootstrap technique is very close to the actual true distribution, right? Because that is the power of Bootstrap. I hope you found this video helpful. I will be doing more lectures on different things like cross-validation, linear regression, and hopefully you can learn statistics from it and do some data mining. Thank you.